Picture this. Somewhere out there, lurking in the frozen darkness beyond Pluto, a world 5 to 10 times the mass of Earth slowly circles our Sun. A planet so distant that it takes between 10 and 20,000 years to complete a single orbit. A world that, if it exists, has been silently shepherding the movements of countless icy objects in the outer reaches of our solar system for billions of years. This isn't science fiction. This is Planet 9, also known as Planet X, and it might be the most significant astronomical discovery waiting to happen. Before we embark on this journey to the edge of everything we know, I'd love to hear from you. Drop a comment and let me know where you're tuning in from tonight, and do you believe there is a Planet X in our solar system? I'd also be incredibly grateful if you gave this video a like and subscribe to join our community of space explorers. Get ready. The hunt for Planet X begins now. Right now, as you're watching this video, some of the world's most brilliant astronomers are engaged in one of the greatest treasure hunts in scientific history. They're scouring the night sky with increasingly powerful telescopes, analysing the orbits of distant objects, and running computer simulations that stretch across billions of years of cosmic time, all in pursuit of a world that may not even exist. The story of our search for hidden worlds starts in the early 1900s, with a man whose passion would consume the final decades of his life and establish one of America's most important astronomical institutions. Percival Lowell was everything you'd expect from a Boston Brahmin of his era, wealthy, educated, and utterly convinced that his mathematical calculations could solve one of astronomy's greatest puzzles. In 1903, Lowell published The Solar System, a work based on lectures he'd given at MIT the previous year. Buried within those pages were the first hints of what would become his magnificent obsession. Lowell had noticed irregularities in the orbit of Uranus, subtle deviations that suggested something massive was tugging at the distant planet from even farther out in the solar system. These weren't random wobbles. They formed a pattern, and patterns in astronomy usually mean something profound is waiting to be discovered. By 1906, Lowell was convinced he could solve what he called the conundrum of Uranus's orbit. He launched an extensive project to search for what he termed Planet X, borrowing the name from French astronomer Gabriel Dalet. The X wasn't the Roman numeral for 10, as many people assume today. It represented the unknown, the mysterious mathematical variable that would complete the equation of our solar system's architecture. Think about the audacity of Lowell's quest. This was an era when photography was still in its infancy, when telescopes were operated by hand-cranked mechanisms, and when the very concept of what lay beyond Neptune was pure speculation. Yet Lowell was so confident in his calculations that he invested his personal fortune in establishing the Lowell Observatory in Flagstaff, Arizona, specifically to find this elusive world. The wealthy businessman transformed himself into a mathematical detective, spending countless hours analysing orbital data, refining his predictions, and calculating where this mysterious planet should appear in the night sky. His passion was infectious, drawing talented astronomers to the isolated observatory on Mars Hill, where they would dedicate their careers to the systematic search for Planet X. In 1915, Lowell published his definitive work on the subject, Memoir on a Trans-Neptunian Planet. This wasn't casual speculation or wishful thinking. It was a rigorous mathematical treatise that laid out precise predictions for where Planet X should be found, how massive it should be, and what its orbital characteristics should look like. Lowell's calculations suggested a world roughly 6 times the mass of Earth, orbiting the Sun at about 43 astronomical units, taking nearly 300 years to complete each circuit. But fate had cruel timing in store for Percival Lowell. In 1916, just as his search was gaining momentum, He died suddenly of a stroke at the age of 61. His mathematical legacy lived on, but the systematic search for Planet X ground to a halt. The observatory he had built continued its work, but without its founder's driving passion and financial backing, the Planet X project was shelved. For over a decade, Lowell's predictions gathered dust while astronomers around the world focused on other mysteries. The search for Planet X seemed destined to become a historical footnote, another example of 19th century astronomical enthusiasm that had outlived its usefulness. That all changed in 1929, when the Lowell Observatory hired a 23-year-old farm boy from Kansas who would accomplish what its founder had died trying to achieve. Clyde Tombaugh arrived in Flagstaff with little formal education, but possessed something far more valuable for the task ahead: unlimited patience and an almost supernatural attention to detail. The observatory had decided to resume the search for Planet X, but they needed someone willing to spend countless hours examining photographic plates through a device called a blink comparator. The blink comparator was ingeniously simple and mind-numbingly tedious to operate. Tombaugh would take photographs of the same region of sky 2 weeks apart, then rapidly alternate between viewing each image. If anything had moved during that time, it would appear to jump back and forth against the background of stationary stars. The technique worked, but it required examining thousands of stars on each photographic plate, looking for the one tiny dot that dared to move. Tombaugh's dedication was extraordinary even by astronomical standards. He later estimated that during his 14-year career at Lowell Observatory, he spent 7,000 hours at the blink comparator eyepiece. That's the equivalent of 63 full working days every single year, staring through an optical instrument, hunting for something that might not even exist. The breakthrough came on February 18th, 1930. Tombaugh was examining photographic plates taken on January 23rd and 29th, when he noticed something that made his heart race. There, among the thousands of stellar points of light, was a tiny dot that had shifted position. It was faint, almost imperceptibly dim, but it was definitely moving with the slow, stately motion characteristic of a distant planet. After obtaining confirmatory photographs to verify the discovery, the Lowell Observatory telegraphed the news to Harvard College Observatory on March 13, 1930. The announcement sent shockwaves through the astronomical community and made headlines around the world. Percival Lowell's prediction had been vindicated. Planet X was real. The discovery sparked a global naming contest that captured public imagination in ways that few astronomical events ever have. The Lowell Observatory received over 1,000 suggestions from around the world, ranging from the mundane to the bizarre. But it was 11-year-old Venetia Burney, a schoolgirl from Oxford, England, who suggested the name that would stick. Pluto, after the Roman god of the underworld, seemed perfectly appropriate for such a dark and distant world. The name held special significance beyond its mythological appropriateness. The first two letters, P and L, were also Percival Lowell's initials, creating a lasting tribute to the man whose obsession had made the discovery possible. The symbol chosen for the new planets ingeniously combined these letters into an astronomical glyph that honoured both the mythological god and the observatory's founder. For 76 years, Pluto held its place as the 9th planet in our solar system. School children memorized its name alongside Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. It was the smallest planet, the coldest planet, and the most mysterious planet, but it was unquestionably a planet in every textbook and classroom around the world. But as our understanding of the outer solar system evolved, Pluto's status became increasingly problematic. Starting in 1992, astronomers began discovering numerous other objects in the same region of space. These Kuiper Belt objects, as they came to be known, included worlds like Eris, which was actually more massive than Pluto itself. If Pluto was a planet, then surely Eris deserved the same classification. And if Eris was a planet, then what about the dozens of other substantial objects being discovered in the outer solar system? The crisis came to a head in 2006 when the International Astronomical Union faced a choice that would reshape our solar system's official roster. They could either expand the definition of planet to include dozens of newly discovered worlds, or they could create a new category that would better reflect the complex reality of what we were finding beyond Neptune. The decision they reached sparked controversy that continues to this day. Pluto was reclassified as a dwarf planet, a designation it shares with Eris, Ceres, Makemake, and Haumea. The reclassification wasn't a demotion based on size alone, but rather recognition that Pluto hadn't cleared its orbital neighbourhood of other objects, a criterion that distinguishes full planets from their smaller cousins. The public reaction was swift and passionate. Pluto had been part of our solar system's family for 3 generations, and millions of people felt genuine emotional attachment to the distant world. Protests, petitions, and even legislative resolutions emerged from various US states declaring Pluto would always be a planet in their jurisdictions. The controversy revealed something profound about humanity's relationship with the cosmos and our deep need for celestial stability in an uncertain universe. But Pluto's reclassification opened the door to something far more intriguing than debates over planetary definitions. With no 9th planet in our solar system, astronomers began to wonder whether there might be something else out there, something much larger and more distant than Pluto, something that could reclaim the title of our solar system's true 9th world. The answer to that question would emerge from one of the most remote and mysterious regions of our cosmic neighbourhood, a vast expanse of icy debris that holds clues to both our solar system's violent past and its potentially surprising present. The Kuiper Belt, that donut-shaped region beyond Neptune where Pluto resides, was about to yield secrets that would reignite the search for Planet X in ways that Percival Lowell could never have imagined. This frozen frontier, stretching from roughly 30 to 55 astronomical units from the Sun, contains millions of objects, ranging from tiny chunks of ice to worlds nearly as large as Pluto itself. Most of these Kuiper Belt objects follow predictable, roughly circular orbits that reflect the orderly processes that shaped the outer solar system billions of years ago. Their movements are governed by well-understood gravitational interactions with Neptune and the other giant planets. But some objects in this region behave very differently. These extreme trans-Neptunian objects follow highly elongated paths that carry them far beyond the main Kuiper Belt, out into regions where the Sun appears as nothing more than a bright star in an ocean of cosmic darkness. Their orbits are so stretched and tilted that they challenge our understanding of how the outer solar system should work. It was the study of these strange, distant objects that would lead to the most compelling evidence yet for a hidden planet in our solar system. A planet that, if it exists, would dwarf Pluto in every measurable way and represent one of the most significant astronomical discoveries in human history. The modern hunt for Planet 9 was about to begin, driven not by the mathematical irregularities that obsessed Percival Lowell, but by a pattern so subtle and unexpected that it took 21st century computers and statistical analysis to reveal its implications. In January 2016, 2 astronomers at the California Institute of Technology dropped a bombshell that would reignite humanity's obsession with hidden worlds. Konstantin Batygin and Mike Brown published research suggesting that something massive was lurking in the outer darkness of our solar system. Not another small icy world, like the dozens already catalogued in the Kuiper Belt, but a genuine planet. A super-Earth weighing 5 to 10 times more than our own world, following a bizarre elongated orbit that takes it 20 times farther from the Sun than Neptune. Their evidence wasn't based on direct observation. No telescope had captured this world's faint glimmer against the cosmic background. Instead, Batygin and Brown had discovered something far more subtle and in many ways more compelling. They had found fingerprints, The story begins with a handful of the most extreme objects known to orbit our Sun. These trans-Neptunian wanderers follow paths so elongated and tilted that they spend most of their time in regions where sunlight is 1,000 times fainter than it is on Earth. Objects like Sedna, discovered in 2003, which takes 11,000 years to complete a single orbit, or 2012 VP-113, whose closest approach to the Sun is still twice as far as Pluto's most distant point. For years, these extreme objects were treated as cosmic curiosities. Interesting, certainly, but not necessarily connected to any larger pattern or process. Each discovery was catalogued, studied, and filed away as another example of the solar system's remarkable diversity. But as more of these distant wanderers were found, something unexpected began to emerge from the data. Brown and Batygin noticed that these far-flung objects weren't randomly distributed throughout space. Their orbits clustered together in ways that seemed to violate the basic principles of celestial mechanics. It was as if some invisible shepherd was herding them into similar paths, aligning their orbits with mathematical precision that couldn't be explained by chance alone. The clustering was subtle but unmistakable when subjected to rigorous statistical analysis. The extreme trans-Neptunian objects tended to reach their closest approach to the Sun in the same general direction. Their orbital planes were tilted at similar angles. Most remarkably, they seemed to avoid certain regions of space entirely, as if something was preventing them from venturing into those forbidden zones. This wasn't the kind of evidence that 19th century astronomers could have detected. It required computer databases capable of tracking hundreds of objects across millions of years of orbital evolution. It demanded statistical techniques that could separate genuine patterns from the random noise that characterizes most astronomical phenomena. Most importantly, it needed theoretical frameworks sophisticated enough to model the gravitational interactions between a hypothetical planet and the complex population of objects in the outer solar system. When Batygin and Brown ran their calculations, the results were startling. A planet with roughly 5 to 10 Earth masses, orbiting between 200 and 800 astronomical units from the Sun, could produce exactly the kind of orbital clustering they were observing. The gravitational influence of such a world would act like a cosmic traffic controller, nudging objects into resonant orbits while clearing out other regions entirely. The mathematical elegance of their solution was compelling, but it raised as many questions as it answered. How could such a massive planet exist in our solar system without being detected? Where did it come from? And why hadn't previous generations of astronomers noticed the orbital patterns that seemed so obvious in hindsight? The first question has a straightforward answer rooted in the physics of detection. Planet 9, if it exists, would be extraordinarily difficult to observe. At its predicted distance, it would receive less than 1/10,000th the sunlight that Earth does. The tiny amount of solar radiation it reflects back toward our telescopes would make it appear dimmer than many asteroids in the inner solar system. Finding it would be like searching for a single black pebble in a darkened football stadium using only a narrow beam flashlight. The second question delves into the chaotic early history of planetary formation. Computer simulations suggest that our solar system once contained additional giant planets that were ejected into interstellar space during gravitational encounters with Jupiter and Saturn. Planet 9 might be a survivor of this ancient cosmic violence, a world that was scattered outward but remained gravitationally bound to the Sun in a highly eccentric orbit. Alternatively, it could be an interloper, a rogue planet that formed around another star and was later captured when our Sun passed through a dense stellar nursery. This scenario would explain why Planet 9's orbit is so different from the roughly circular paths followed by the other planets. It would be a permanent immigrant in our solar system, forever marked by its alien origins. The third question highlights one of the most fascinating aspects of modern astronomy. The orbital patterns that pointed toward Planet 9 had been hiding in plain sight for decades, but they only became apparent when astronomers developed the tools to analyze large datasets statistically. It's a reminder that some of the universe's deepest secrets might be concealed not in distant galaxies or exotic phenomena, but in the familiar objects that surround us. As news of the Planet 9 hypothesis spread through the astronomical community, it triggered intense debate and scrutiny. The evidence was intriguing, but extraordinary claims demand extraordinary proof. Critics pointed out that the statistical significance of the orbital clustering, while suggestive, fell short of the rigorous standards typically required for major astronomical discoveries. Some researchers argued that observational bias might explain the apparent clustering. The extreme trans-Neptunian objects are so faint and slow-moving that they are only detectable when they're relatively close to the Sun. This creates a natural selection effect that could artificially cluster their observed positions without requiring any gravitational shepherd. Others suggested that the clustering might be a statistical fluke, a pattern that appears meaningful but results from the limited sample size of known extreme objects. With only a handful of these distant worlds catalogued, it's possible that future discoveries will reveal a more random distribution that eliminates the need for Planet 9 entirely. The debate intensified in 2020 when two major surveys published results that challenged the Planet 9 hypothesis. The Outer Solar System Origins Survey and the Dark Energy Survey had discovered hundreds of new trans-Neptunian objects using carefully designed observation strategies that minimized potential biases. When these objects were analyzed, the orbital clustering that had pointed toward Planet 9 seemed to disappear. Dr. Samantha Lawler, one of the lead researchers on these surveys, argued that the Planet 9 hypothesis does not hold up to detailed observations. She pointed out that the original analysis was based on just 14 objects, while Neptunian objects. With this much larger sample size, the new surveys had catalogued over 800 trans. The statistical evidence for clustering became far less compelling. But the Planet 9 advocates weren't ready to surrender. In 2021, a team led by graduate student Amir Siraj published new analysis that expanded the sample of relevant objects from 11 to 51 by including trans-Neptunian objects that previous studies had ignored. Their calculations suggested that there was only a 1 in 1,000 chance that the orbital alignments were random, providing the strongest statistical evidence yet for Planet 9's existence. The controversy illustrates one of the fundamental challenges facing modern astronomy. Unlike laboratory sciences where experiments can be repeated under controlled conditions, astronomy relies on observations of phenomena that unfold across cosmic timescales. We get only one solar system to study, and we must infer its history and hidden components from incomplete and potentially biased data. The search for Planet 9 has also revealed the extraordinary complexity of gravitational dynamics in the outer solar system. Computer simulations capable of modelling the evolution of thousands of objects over billions of years have become essential tools for understanding how planetary systems develop and change. These calculations require massive computational resources and sophisticated algorithms that push the boundaries of what's possible with current technology. The simulations paint a picture of the outer solar system as a dynamic, ever-changing environment where objects can hop between different orbital resonances over millions of years. A trans-Neptunian object might spend eons in a stable orbit before a close encounter with Neptune sends it careening into the outer darkness. The gravitational influence of a distant Planet 9 would add another layer of complexity to this cosmic choreography, creating resonances and instabilities that could explain some of the strange orbital architectures we observe. Perhaps the most intriguing aspect of the Planet 9 hypothesis is what it suggests about planetary formation and migration. If confirmed, it would provide direct evidence that our solar system's current configuration is not its original state. The planets we see today are the survivors of a much more chaotic early period when gravitational interactions regularly scattered worlds into new orbits or ejected them entirely. This dynamic view of planetary system evolution has profound implications for understanding other solar systems discovered around nearby stars. Many of these exoplanetary systems contain hot Jupiters, massive worlds that orbit extremely close to their parent stars. The existence of these planets puzzled astronomers for years because they couldn't have formed so close to their stars where temperatures would have prevented the accumulation of solid building blocks. The solution lies in planetary migration. These hot Jupiters likely formed farther out in their systems before spiraling inward due to gravitational interactions with the disk of gas and dust from which they condensed. Planet 9, if it exists, might be our solar system's example of the opposite process, a world that was scattered outward rather than inward during the early epochs of planetary formation. The hunt for Planet 9 has also spurred development of new observational techniques and technologies. Traditional methods of planetary discovery rely on detecting the wobble that orbiting planets induce in their parent stars, or the slight dimming that occurs when planets transit in front of stellar disks. But Planet 9 is too distant and dim to be found using these approaches. Instead, astronomers have turned to wide-field surveys that repeatedly image large portions of the sky, looking for objects that move slowly against the background stars. These surveys must process enormous amounts of data, identifying genuine moving objects, while filtering out cosmic rays, asteroids, and other sources of false signals. Machine learning algorithms have become essential tools for managing this data deluge and identifying the subtle patterns that might reveal Planet 9's location. The challenge is compounded by the fact that Planet 9's orbital period could be anywhere from 10,000 to 20,000 years. Even if astronomers detect it moving across the sky, it might take decades of observations to determine its orbit with sufficient precision to confirm its identity. This is astronomy on the longest possible timescales, requiring patience and persistence that span entire scientific careers. Current estimates suggest that if Planet 9 exists, it's most likely located in the southern sky, in regions that are difficult or impossible to observe from most northern hemisphere observatories. This has focused attention on facilities in Chile, Australia, and other southern locations that can access these crucial portions of the sky. The systematic survey of the southern sky represents one of the largest coordinated observational projects in modern astronomy. Yet despite years of intensive searching, Planet 9 remains tantalizingly out of reach. Every survey that fails to detect it places new constraints on its possible properties and location. If it exists, it must be smaller, more distant, or darker than initial estimates suggested. Each non-detection narrows the parameter space where Planet 9 could be hiding, but also makes the remaining possibilities increasingly difficult to test. The absence of detection has led some researchers to propose alternative explanations for the orbital clustering that inspired the Planet 9 hypothesis. Modified theories of gravity, such as MOND, might explain the observed orbital patterns without requiring an additional planet. Collectively, a disk of smaller objects in the outer solar system could produce similar gravitational effects to a single massive world. Others have suggested that Planet 9 might not be a planet at all, but rather a primordial black hole, a remnant from the early universe that became gravitationally bound to our solar system. Such an object would be virtually impossible to detect directly, but could produce the same gravitational effects as a conventional planet. This speculative possibility highlights how the Planet 9 hypothesis has pushed astronomers to consider scenarios that would have seemed absurd just a few decades ago. The search continues with ever more sophisticated instruments and techniques. Ground-based surveys are being complemented by space-based observations that can access wavelengths of light blocked by Earth's atmosphere. Infrared telescopes might be able to detect the faint thermal emission from Planet 9's surface, providing an alternative to relying on reflected sunlight. Most exciting of all is the imminent arrival of the Vera Rubin Observatory, a revolutionary facility designed specifically for the kind of wide-field, time-domain astronomy needed to find moving objects in the outer solar system. When it begins operations, the Rubin Observatory will scan the entire southern sky every few nights, generating an unprecedented database of celestial motions that should finally provide definitive answers about Planet 9's existence. The implications of discovering Planet 9 would extend far beyond our own solar system. It would validate theoretical models of planetary formation and migration that have been developed to explain the properties of exoplanetary systems. It would demonstrate that our solar system is more typical than previously thought, containing examples of the same dynamical processes that have shaped planetary systems throughout the galaxy. Perhaps most importantly, it would remind us that even our own cosmic neighborhood still holds mysteries waiting to be solved. In an era when space telescopes can image galaxies billions of light years away and detect gravitational waves from colliding black holes, the possibility that a major planet remains undiscovered in our own solar system serves as a humbling reminder of how much we still have to learn about the universe around us. The story of Planet 9 embodies everything that makes astronomy compelling. It combines rigorous mathematical analysis with cutting-edge observational techniques. It connects the early history of our solar system with its present-day structure. Most importantly, it demonstrates that the universe is still capable of surprising us, that new discoveries await those patient enough to look carefully at the data and bold enough to follow the evidence wherever it leads. Whether Planet 9 exists or not, the search for it has already transformed our understanding of the outer solar system and the complex gravitational processes that continue to shape planetary orbits billions of years after formation. The hunt continues, driven by the tantalizing possibility that somewhere in the darkness beyond Neptune, a world waits to be found that will once again expand our conception of the solar system we call home. As the astronomical community wrestles with these competing interpretations, the search for Planet 9 has evolved into something resembling a cosmic game of hide-and-seek played on the grandest possible scale. The challenge isn't just finding a needle in a haystack, it's finding a needle in a haystack the size of the outer solar system, where the needle might not even exist and where looking in the wrong place could waste years of precious observing time. The technical hurdles facing Planet 9 hunters are staggering. Consider the sheer vastness of the search area. If Planet 9 follows the kind of elongated orbits predicted by Batygin and Brown, it could currently be located anywhere within a region of sky covering thousands of square degrees. That's equivalent to searching an area more than 10 times the size of the full moon, looking for an object that would appear as nothing more than a faint dot moving almost imperceptibly against the stellar background. The motion itself presents another layer of complexity. Planet 9, if it exists, would crawl across the sky so slowly that detecting its movement requires observations separated by months or even years. An object at 400 astronomical units from the Sun would appear to move at roughly the same angular rate as the hour hand on a clock, assuming you could somehow see that hour hand from several miles away. This glacial pace means that distinguishing Planet 9 from background stars demands extraordinary patience and precision. Modern planet hunters have developed ingenious strategies to overcome these challenges. Rather than randomly scanning the sky and hoping to stumble across their target, they use sophisticated computer models to predict where Planet 9 is most likely to be found. These simulations incorporate everything we know about the gravitational dynamics of the outer solar system, the orbital properties of extreme trans-Neptunian objects, and the observational constraints placed by previous unsuccessful searches. The models paint a complex picture of probability landscapes across the sky, with some regions marked as highly likely hunting grounds, while others are effectively ruled out. the most promising search areas tend to be located far from the galactic plane, where fewer background stars create confusion, and in regions of sky accessible to the world's most powerful telescopes during optimal observing conditions. Dr. Mike Brown, one of Planet Nine's most ardent advocates, has spent the better part of a decade systematically working through these predicted locations. His team uses the Subaru telescope in Hawaii, one of the most sensitive instruments available for this kind of deep sky survey work. Night after night, they image carefully selected patches of sky, building up a database of stellar positions that can reveal the subtle movements characteristic of distant solar system objects. The work is methodical and often frustrating. Most nights yield nothing more than images of empty space populated by stars that haven't moved since the last observation. But occasionally, something interesting appears in the data. A faint point of light that seems to have shifted position. A potential candidate that sends excitement rippling through the research team until follow-up observations reveal it to be a distant asteroid, a background galaxy, or simply an artifact of the imaging process. Each false alarm teaches the hunters something valuable about the challenges they face and the techniques they need to refine. The process has evolved into a sophisticated blend of automated detection algorithms and human pattern recognition, with computers flagging potential candidates and experienced astronomers making the final determination about which objects deserve further investigation. The false alarms also highlight one of the most maddening aspects of the Planet 9 search. The outer solar system is populated by thousands of objects that could potentially masquerade as the missing planet during preliminary observations. Distant asteroids, Kuiper belt objects, and even main belt asteroids, seen at unusual angles, can all produce the kind of slow motion that characterizes trans-Neptunian objects, distinguishing Planet 9 from this cosmic background noise requires multiple observations spread across months or years, followed by careful orbital calculations that can determine whether a newly detected object follows the kind of path expected for the hypothetical ninth planet. This process can take longer than the time available during a single observing season, creating logistical challenges that complicate even the most well-funded search programs. The international nature of modern astronomy has brought together research teams from around the world in pursuit of Planet 9. Projects like the Dark Energy Survey, originally designed to study cosmic acceleration and dark matter, have contributed valuable data about trans-Neptunian objects discovered as byproducts of their primary mission. The Catalina Sky Survey and linear programs established to hunt for potentially hazardous asteroids have similarly provided serendipitous discoveries that inform our understanding of the outer solar system's population. These collaborative efforts have revealed just how much we still don't know about the distant reaches of our own cosmic neighborhood. Every survey discovers new objects that challenge existing models of how the outer solar system should be organized. Some follow predictable orbits that fit neatly into theoretical frameworks developed over decades of research. Others display bizarre characteristics that demand entirely new explanations. Take the object designated 2018 VG18, nicknamed Farut by its discoverers. This tiny world orbits the Sun at an average distance of more than 120 astronomical units, making it one of the most distant objects ever found in our solar system. Its discovery required some of the most sensitive detection techniques available to modern astronomy, and its existence raises questions about how such distant objects could have formed and survived in their current locations. Even more mysterious is 2012 VP113, an object whose orbit never brings it closer to the Sun than 80 astronomical units. This places it in a category that astronomers call inner Oort cloud objects, inhabitants of a region so distant that they're barely influenced by the gravitational pull of the known planets. The existence of such objects suggests that the outer solar system contains populations of bodies that formed under conditions very different from those that shaped the inner planets. These extreme objects provide crucial test cases for theories about Planet Nine's gravitational influence. If the hypothetical ninth planet exists, it should leave detectable fingerprints in the orbital characteristics of the most distant known objects. Computer simulations can predict exactly what kinds of orbital modifications Planet 9 should produce, creating a roadmap for distinguishing between objects that have been influenced by the hidden world and those that haven't. The simulations reveal a fascinating picture of gravitational choreography playing out across billions of years. Objects that venture too close to Planet 9's orbit get scattered into new trajectories, while those that maintain safe distances can remain stable for cosmic ages. The result is a complex pattern of orbital resonances and instabilities that create structure in what might otherwise appear to be a random distribution of distant objects. Some of the most compelling evidence for Planet 9 comes from objects that seem to avoid certain regions of orbital space entirely. These forbidden zones appear in the data as gaps where objects should exist but don't, creating negative space that's just as informative as positive detections. The pattern of these gaps matches theoretical predictions for how Planet 9's gravity would clear out certain types of orbits, while leaving others undisturbed. But the absence of evidence isn't necessarily evidence of absence, and critics of the Planet 9 hypothesis have proposed alternative explanations for these apparent orbital gaps. Selection effects could bias observations toward detecting objects in certain orbital configurations while missing others. The limited sensitivity of current surveys might create artificial gaps in regions where objects are too faint to detect. Even the seasonal availability of different portions of the sky can influence which objects are discovered and which remain hidden. The debate has intensified as increasingly sophisticated statistical techniques are applied to the growing catalogue of trans-Neptunian objects. Modern surveys discover dozens of new objects each year, providing fresh data that can either support or challenge the Planet 9 hypothesis. Each new discovery shifts the statistical balance slightly, sometimes strengthening the case for orbital clustering and sometimes weakening it. Dr. Pedro Bernardinelli, a researcher at the University of Pennsylvania, has been at the forefront of efforts to expand the census of distant solar system objects. His team has used data from the Dark Energy Survey to identify over 300 new trans-Neptunian objects, more than doubling the number of known inhabitants of the outer solar system. This expanded dataset provides unprecedented statistical power for testing theories about Planet 9's influence. The results of these expanded surveys paint a complex picture that doesn't easily support either side of the Planet 9 debate. Some aspects of the orbital distribution match theoretical predictions for a massive distant planet, while others seem more consistent with random distributions or alternative explanations. The statistical significance of the clustering, while still present, has decreased as more objects have been discovered. This evolving picture reflects one of the fundamental challenges facing modern astronomy. The universe rarely provides clear, unambiguous answers to our questions. Instead, it offers subtle patterns embedded in noisy data, requiring sophisticated analysis techniques and careful consideration of potential systematic errors. The Planet 9 controversy exemplifies this challenge, presenting evidence that's suggestive but not quite definitive. Meanwhile, theorists have been exploring what Planet 9 might actually be if it does exist. The original hypothesis suggested a super-Earth, a type of planet common in other star systems but absent from our own. Such a world would have formed from the same disk of gas and dust that gave birth to the other planets, but would have been scattered outward during the chaotic early epochs of solar system evolution. Computer simulations of planetary formation suggest that our solar system likely contained additional giant planets that were ejected into interstellar space during gravitational encounters with Jupiter and Saturn. Planet 9 might be a survivor of this ancient cosmic violence, a world that was scattered outward but remained gravitationally bound to the Sun. This scenario would explain why its orbit is so different from the roughly circular paths followed by the other planets. Alternative formation scenarios propose that Planet 9 might be a captured rogue planet, a world that formed around another star and was later adopted by our solar system. This possibility has gained attention as astronomers have discovered evidence for large numbers of free-floating planets drifting through interstellar space. If our Sun passed through a dense stellar nursery early in its history, it might have gravitationally captured one of these wandering worlds. The capture scenario would explain some of Planet 9's most puzzling characteristics, particularly the high inclination and retrograde motion suggested by some orbital models. A planet that formed around another star would retain the orbital characteristics it acquired in its birth system, creating a permanent signature of its alien origins. More exotic possibilities include the suggestion that Planet 9 might not be a conventional planet at all, but rather a primordial black hole left over from the early universe. Such objects, if they exist, would be extraordinarily difficult to detect directly, but could produce the same gravitational effects as a massive planet. The black hole hypothesis represents the kind of creative thinking that characterizes modern theoretical astronomy, where conventional explanations give way to increasingly speculative possibilities. The primordial black hole scenario highlights how the Planet 9 search has pushed researchers to consider phenomena that would have seemed absurd just a few decades ago. The hypothesis requires that our solar system captured a black hole with roughly 5 Earth masses, a process that would have required extraordinary circumstances during the Sun's formation. While theoretically possible, such scenarios stretch the boundaries of plausibility and require evidence far beyond what's currently available. More conventional explanations focus on the possibility that Planet 9 is a failed gas giant, a world that began accumulating a massive atmosphere but was scattered outward before it could complete the process. Such objects might have solid cores similar to Neptune or Uranus, but lack the thick gaseous envelopes that characterize the outer planets. This scenario would place Planet 9 in a category intermediate between rocky super-Earths and full gas giants. The failed gas giant hypothesis makes specific predictions about Planet 9's physical characteristics that could be tested if the planet is ever directly observed. Such a world would likely appear dark and cold, reflecting very little sunlight and emitting minimal thermal radiation. Its atmosphere, if it has one, would probably consist of hydrogen and helium retained from the original solar nebula, creating a composition more similar to the giant planets than to rocky worlds like Earth. These theoretical investigations have revealed the remarkable diversity of possible outcomes during planetary formation. The same basic process that created our solar system's familiar roster of planets could have produced radically different results under slightly altered conditions. Planet 9, regardless of its specific nature, would represent a fossil record of these early evolutionary processes. The search techniques being developed for Planet 9 have applications that extend far beyond our own solar system. The methods used to detect slow-moving objects against stellar backgrounds are directly relevant to finding Earth-like planets orbiting nearby stars. The statistical techniques developed to analyze orbital clustering could help identify the gravitational signatures of planets in other systems that are too small or distant to detect directly. Advanced imaging techniques originally developed for Planet 9 searches are being adapted for studies of galaxy formation and dark matter distribution. The same algorithms that filter out false positives in trans-Neptunian object surveys can identify genuine astronomical signals in other types of observational data. The technological spillovers from the Planet 9 search illustrate how fundamental research often produces unexpected benefits across multiple scientific disciplines. The most significant advance in Planet 9 detection capabilities will come from the Vera Rubin Observatory, currently under construction in Chile. This revolutionary facility will conduct the most comprehensive survey of the southern sky ever attempted, repeatedly imaging the same regions with unprecedented sensitivity and precision. The observatory's enormous camera and sophisticated data processing systems are specifically designed for the kind of time-domain astronomy needed to detect moving objects in the outer solar system. When the Rubin Observatory begins full operations, it will generate approximately 20 terabytes of data every night, creating a database of celestial motions that will dwarf all previous astronomical surveys combined. The facility's automated detection algorithms will identify millions of moving objects, ranging from nearby asteroids to the most distant inhabitants of the outer solar system. If Planet 9 exists anywhere within the survey area, the Rubin Observatory should find it within the first few years of operation. The observatory's impact on Planet 9 research extends beyond simple detection capabilities. Its systematic survey approach will provide the first truly unbiased census of trans-Neptunian objects, eliminating many of the selection effects that have complicated previous analyses. This comprehensive dataset will finally allow astronomers to test the Planet 9 hypothesis with the statistical rigor that such extraordinary claims demand. Dr. Lynn Jones, a researcher involved in planning the Rubin Observatory's survey strategy, estimates that the facility will discover approximately 40,000 new trans-Neptunian objects during its decade-long mission. This represents a 100-fold increase in the known population of these distant worlds, providing unprecedented insight into the structure and evolution of the outer solar system. The flood of new data from Rubin Observatory will require equally sophisticated analysis techniques to extract meaningful scientific conclusions. Machine learning algorithms are being developed specifically to identify patterns in large astronomical datasets, automating much of the tedious work that currently requires human oversight. These systems can process vast quantities of observational data, flagging unusual objects or orbital configurations that merit further investigation. The combination of Rubin Observatory's observational capabilities and advanced analysis techniques represents a quantum leap in humanity's ability to explore the outer solar system. Within the next decade, we should have definitive answers about Planet 9's existence and a comprehensive understanding of the distant objects that populate the furthest reaches of our cosmic neighborhood. Whether Planet 9 is discovered or definitively ruled out, the search has already revolutionized our understanding of planetary system architecture and evolution. The investigation has revealed the outer solar system to be a far more dynamic and complex environment than previously imagined, populated by objects whose orbits preserve records of violent events that occurred billions of years ago. The techniques developed for Planet 9 research are being applied to studies of exoplanetary systems, where similar gravitational signatures might reveal the presence of distant planets around other stars. The theoretical frameworks developed to understand orbital clustering in our own solar system provide tools for interpreting the complex planetary architectures discovered by space-based telescopes like Kepler and TESS. Most importantly, the Planet 9 saga demonstrates that our own solar system still holds fundamental secrets waiting to be discovered. In an era when we can image black holes in distant galaxies and detect gravitational waves from cosmic collisions, the possibility that a major planet remains hidden in our own cosmic backyard serves as a humbling reminder of how much we still have to learn about the universe around us. The search continues with renewed intensity and unprecedented technological capabilities. Every clear night brings new opportunities to probe the darkness beyond Neptune, seeking the faint glimmer that might betray the presence of our solar system's most elusive resident. The universe guards its secrets jealously, but human curiosity and ingenuity have proven remarkably effective at prying loose even the most well-hidden cosmic mysteries. Somewhere in the vast darkness beyond the orbit of Neptune, the truth about Planet 9 waits to be discovered. Whether that truth involves a massive hidden world reshaping the architecture of our solar system, or a more mundane explanation for the orbital patterns that have captivated astronomers for nearly a decade, the answer will fundamentally change our understanding of the cosmic environment we call home. The clock is ticking toward resolution. Advanced surveys are methodically scanning the sky, computer simulations are refining predictions about where Planet 9 might be hiding, and revolutionary new observatories are preparing to bring unprecedented sensitivity to bear on this cosmic mystery. Within the next few years, we should finally know whether our solar system contains a ninth planet worthy of the name, or whether the patterns that suggested its existence will dissolve under more careful scrutiny. Either outcome will mark a watershed moment in planetary science, closing one chapter in humanity's long quest to understand our place in the cosmos, while simultaneously opening new avenues for exploration and discovery. The hunt for Planet 9 represents everything that makes astronomy compelling. The marriage of theoretical prediction and observational verification, the patient accumulation of evidence across years and decades, and the tantalizing possibility that the next observation might reveal something that changes everything we thought we knew about the universe around us. The tantalizing prospect of finally resolving this cosmic mystery has transformed Planet 9 from a theoretical curiosity into one of astronomy's most urgent quests. But as the search intensifies and technology advances, researchers are grappling with a fundamental question that goes beyond simple detection. What exactly are they looking for? The answer depends on which formation scenario proves correct, and each possibility paints a dramatically different picture of what Planet 9 might actually be. If it formed alongside the other planets before being scattered outward, we're dealing with what astronomers call a super-Earth, a rocky world perhaps 5 to 10 times more massive than our own planet, with a solid surface beneath whatever thin atmosphere it might retain in the frigid depths of the outer solar system. Such a world would represent a missing link in our solar system's planetary family. Super-Earths are the most common type of planet discovered around other stars, yet our solar system lacks any example of these intermediate mass worlds. They're too large to be terrestrial planets like Earth or Mars, but too small to be gas giants like Neptune or Uranus. Finding one in our own cosmic backyard would fill a conspicuous gap in the planetary bestiary. A super-Earth Planet 9 would likely possess a rocky composition similar to Earth, but compressed under the intense gravitational pressure created by its additional mass. The surface gravity would be punishing by human standards, perhaps 2 or 3 times stronger than what we experience on Earth. Any hypothetical visitor to such a world would find themselves struggling against a gravitational field that makes every movement feel like carrying an invisible backpack loaded with rocks. The temperature on a super-Earth Planet 9 would be almost incomprehensibly cold. At 400 astronomical units from the Sun, the surface would receive less than 1/16,000th the solar energy that reaches Earth. Temperatures would hover around -230 degrees Celsius, cold enough to freeze nitrogen solid and create landscapes of exotic ices that have no terrestrial equivalent. But the super-Earth scenario represents just one possibility among several competing theories about Planet 9's nature and origin. Alternative formation models suggest we might be dealing with something far more exotic, a failed gas giant that began accumulating a massive atmosphere before being ejected from the inner solar system. This failed giant scenario envisions Planet 9 as a world that started life much closer to the Sun, perhaps in the region where Jupiter and Saturn now orbit. During the chaotic early epochs of planetary formation, gravitational interactions with the developing gas giants could have scattered this protoplanet outward before it could complete its transformation into a full-fledged gas giant. A failed gas giant would possess a solid core similar to Neptune or Uranus, surrounded by whatever remnants of its original atmosphere managed to survive the violent ejection process. The result would be a hybrid world, neither fully terrestrial nor fully gaseous, occupying a unique evolutionary niche that reflects the turbulent history of solar system formation. The atmospheric characteristics of such a world would depend critically on the details of its ejection and subsequent evolution. If Planet 9 retained a significant hydrogen and helium envelope, it might appear as a smaller, colder version of Neptune, with dynamic weather systems driven by internal heat sources rather than solar radiation. Alternatively, if atmospheric escape processes stripped away most of its original envelope, it might more closely resemble a super-Earth with only a thin residual atmosphere. Perhaps the most intriguing possibility is that Planet 9 represents something even more exotic, a captured rogue planet that formed around another star entirely. This scenario would make our hypothetical ninth world a permanent immigrant in our solar system, forever marked by the alien conditions of its birth environment. The galaxy is thought to contain billions of rogue planets, worlds that were ejected from their birth systems during planetary formation or later gravitational encounters. These cosmic wanderers drift through interstellar space, carrying with them the chemical signatures of their original stellar environments. If our Sun captured one of these nomadic worlds during its early history, the result would be a planet with characteristics unlike anything else in our solar system. A captured rogue planet might display isotopic ratios or chemical compositions that reflect the different stellar nucleosynthesis processes that occurred in its birth system. Its orbital characteristics would preserve permanent evidence of the capture event, following a path that bears no resemblance to the roughly circular orbits of the native-born planets. The capture process itself would have required extraordinary circumstances. Rogue planets move through interstellar space at high velocities, making gravitational capture extremely difficult under normal conditions. The process would likely have required the presence of a dense gas disk around the young Sun, which could have dissipated the rogue planet's kinetic energy and allowed it to settle into a bound orbit. This scenario gains credibility from recent discoveries of exoplanetary systems with highly unusual architectures. Astronomers have found planets with retrograde orbits, worlds that circle their stars in the opposite direction from their stellar rotation. They've discovered planets with extreme orbital inclinations, tilted at impossible angles relative to their system's equatorial plane. These observations suggest that planetary capture, while rare, is not impossible. The implications of a captured Planet 9 would extend far beyond our own solar system. It would demonstrate that planetary systems can exchange members across interstellar distances, creating a kind of galactic ecology where worlds migrate between different stellar environments. This process could have profound consequences for the development of life, potentially spreading organic compounds or even living organisms between star systems. But not all researchers are convinced that Planet 9 requires such exotic explanations. A growing body of work suggests that the orbital clustering that inspired the Planet 9 hypothesis might result from much more mundane causes that don't require any additional massive objects in the outer solar system. Dr. Anne-Marie Madigan at the University of Colorado has proposed an alternative mechanism based on the collective gravitational effects of the trans-Neptunian objects themselves. Her models suggest that a disk of smaller objects in the outer solar system could gravitationally interact with each other over millions of years, eventually producing the kind of orbital clustering that has been attributed to Planet 9. This collective effect would work like a gravitational democracy, where no single object dominates the dynamics, but the combined influence of many smaller bodies creates large-scale patterns in orbital distribution. The process would be subtle and slow, requiring millions of years to produce detectable effects, but it could potentially explain the observed clustering without invoking any hidden massive planet. The disk model makes specific predictions about how the clustering should evolve over time and what additional patterns should be observable if the mechanism is correct. These predictions can be tested against the growing database of trans-Neptunian objects, providing a way to distinguish between the disk scenario and the Planet 9 hypothesis. Other researchers have focused on the possibility that observational biases are creating artificial clustering where none actually exists. The trans-Neptunian objects used to infer Planet 9's existence are extraordinarily faint and difficult to observe. They can only be detected when they're relatively close to the Sun, creating a natural selection effect that might artificially concentrate discoveries in certain orbital configurations. Dr. Corey Shankman at the University of Victoria has conducted detailed simulations of how observational biases might affect the apparent distribution of trans-Neptunian objects. His work suggests that the clustering could result from the seasonal availability of different regions of sky, combined with the limited sensitivity of current surveys to very distant objects. The bias question highlights one of the fundamental challenges facing modern astronomy, distinguishing between real astrophysical phenomena and artifacts created by the limitations of our observational techniques. Every telescope has blind spots, every survey has selection effects, and every dataset reflects the specific circumstances under which it was collected. Resolving these competing explanations requires not just more observations, but better observations that can overcome the systematic biases that plague current surveys. The Vera Rubin Observatory represents a crucial step in this direction, offering unprecedented sky coverage and sensitivity that should finally provide the unbiased dataset needed to test the Planet 9 hypothesis definitively. Meanwhile, some theorists have proposed even more radical alternatives that challenge our understanding of gravity itself. Modified Newtonian dynamics, or MOND, suggests that the laws of gravity might behave differently at very low accelerations, such as those experienced by objects in the outer solar system. Under MOND, the orbital clustering attributed to Planet 9 could result from subtle modifications to gravitational physics, rather than the presence of any additional massive object. This scenario would make the outer solar system a testing ground for exotic theories of gravity that were originally developed to explain the rotation curves of galaxies and the large-scale structure of the universe. The MOND explanation for Planet 9 represents the kind of bold theoretical thinking that occasionally revolutionizes science. If correct, it would suggest that our understanding of gravity, one of the most fundamental forces in nature, remains incomplete even within our own solar system. The implications would extend far beyond planetary science, potentially affecting everything from satellite navigation to cosmological models of dark matter. However, MOND faces significant challenges when applied to solar system dynamics. The theory was designed to address phenomena at galactic scales, and its predictions for planetary motions don't always match detailed observations. Most astronomers remain skeptical that modified gravity can explain the Planet 9 evidence without creating conflicts with other well-established aspects of celestial mechanics. The diversity of proposed explanations reflects the complexity of the evidence and the high standards required for extraordinary claims in astronomy. Each alternative explanation makes specific predictions that can be tested against observational data, creating a competition between different theoretical frameworks that will ultimately be resolved by better observations. This scientific process exemplifies how astronomy advances through the interplay between theory and observation. Hypotheses are proposed based on limited data, predictions are made, new observations are obtained, and theories are refined or abandoned based on how well they match reality. The Planet 9 controversy represents this process in action, with multiple competing explanations vying for acceptance based on their ability to explain the available evidence. The resolution of this competition will likely come from the unprecedented dataset that the Vera Rubin Observatory will generate over the next decade. by discovering tens of thousands of new trans-Neptunian objects and providing the first truly comprehensive survey of the outer solar system, Rubin will either confirm the orbital clustering that points toward Planet 9 or reveal it to be an artifact of incomplete sampling. Dr. Mario Duric, who leads the Rubin Observatory's data management efforts, describes the facility's impact on Planet 9 research as potentially revolutionary. The systematic, unbiased survey approach will eliminate many of the selection effects that have complicated previous analyses, while the enormous increase in sample size will provide statistical power that dwarfs anything currently available. The implications of resolving the Planet 9 mystery extend far beyond academic satisfaction. If Planet 9 exists, its discovery would fundamentally change our understanding of how planetary systems form and evolve. It would provide direct evidence that our solar system's current architecture reflects a violent early history of planetary migration and ejection. Such a discovery would also validate theoretical models that predict widespread planetary migration in young stellar systems. These models suggest that most exoplanetary systems have experienced similar episodes of chaos and reorganization, making our solar system's apparent stability the exception rather than the rule. The existence of Planet 9 would also raise fascinating questions about its potential for harboring life or interesting chemistry. While the extreme cold and distance from the Sun would preclude Earth-like biology, the planet might possess internal heat sources that could maintain subsurface liquid water or drive exotic chemical processes. Recent discoveries have revealed that many of the outer solar system's moons harbour subsurface oceans heated by tidal forces or radioactive decay. Europa, Enceladus, and Titan all maintain liquid water beneath their frozen surfaces, creating environments that might support microbial life. A massive Planet 9 could generate similar internal heating, potentially creating habitable niches in the most unlikely locations. The discovery would also transform Planet 9 into one of the most important targets for future space missions. While the enormous distance would make any mission extraordinarily challenging, the scientific payoff would justify the investment required to reach such a remote and mysterious world. Conversely, if Planet 9 doesn't exist, the failure to find it would be equally significant for our understanding of solar system dynamics. It would suggest that the orbital clustering of extreme trans-Neptunian objects results from more subtle processes that we're only beginning to understand, opening new avenues for research into the complex gravitational interactions that shape planetary system architecture. The absence of Planet 9 would also highlight the importance of observational biases and selection effects in astronomical research. It would serve as a cautionary tale about the dangers of drawing strong conclusions from limited datasets, emphasizing the need for comprehensive, unbiased surveys in all areas of astronomy. Regardless of the outcome, the Planet 9 search has already advanced our understanding of the outer solar system in unprecedented ways. The investigation has revealed the remarkable diversity of objects inhabiting the furthest reaches of our cosmic neighborhood, from tiny ice balls to substantial dwarf planets following bizarre orbital paths. The search has also driven technological and methodological advances that benefit astronomy more broadly. The statistical techniques developed to analyze planetary systems and orbital clustering are being applied to studies of exoplanet and galaxy formation. The observational strategies pioneered for detecting slow-moving, distant objects are finding applications in searches for near-Earth asteroids and studies of stellar proper motions. Perhaps most importantly, the Planet 9 saga demonstrates that our own solar system continues to surprise us with new discoveries and mysteries. In an era when we can detect planets around stars hundreds of light years away and image the supermassive black hole at the center of our galaxy, the possibility that a major planet remains hidden in our own cosmic backyard serves as a humbling reminder of how much we still have to learn. The search represents everything that makes astronomy compelling: the marriage of careful observation and theoretical insight, the patient accumulation of evidence across years and decades, and the tantalizing possibility that the next observation might revolutionize our understanding of the universe around us. As advanced surveys continue their methodical scan of the southern sky and computer simulations refine their predictions about Planet Nine's location and properties, we stand on the threshold of resolving one of the solar system's greatest mysteries. The answer, whatever it turns out to be, will mark a watershed moment in planetary science and fundamentally change how we understand the cosmic environment we call home. The universe rarely yields its secrets easily, but human curiosity and ingenuity have proven remarkably effective at extracting truth from even the most challenging observational puzzles. Whether Planet 9 exists as a massive world reshaping our solar system's architecture or represents a more subtle phenomenon, we're only beginning to understand. The resolution of this mystery will advance our knowledge in ways that ripple through multiple areas of astronomical research. Every clear night brings new opportunities to probe the darkness beyond Neptune, seeking answers to questions that have captivated astronomers for nearly a decade. The telescopes are ready, the analysis techniques are refined, and the theoretical frameworks are in place. All that remains is for the universe to reveal whether our solar system contains a ninth world worthy of the name, or whether the patterns that suggested its existence will dissolve under more careful scrutiny. In laboratories and observatories around the world, dedicated researchers continue their patient vigil, knowing that they're participating in one of astronomy's most significant investigations. They're not just searching for another planet, but probing the fundamental processes that shaped our solar system and countless others throughout the galaxy. The clock ticks toward resolution, measured not in hours or days, but in observing seasons and survey completions. Advanced instruments are methodically mapping the sky with unprecedented precision, building databases that will either confirm Planet 9's existence or provide definitive evidence for its absence. The answer waits in the data, hidden among millions of stellar positions and orbital measurements, ready to be extracted by the next generation of analysis algorithms. When that answer finally emerges, it will close one chapter in humanity's quest to understand our place in the cosmos, while simultaneously opening new avenues for exploration and discovery. The hunt for Planet 9 embodies the best aspects of scientific investigation: rigorous methodology, creative theorizing, and the courage to pursue extraordinary possibilities wherever the evidence leads. Whether we're on the verge of discovering our solar system's most distant major world, or learning important lessons about the limitations of astronomical inference, the Planet 9 search represents a defining moment in planetary science. The outcome will influence how we think about planetary formation, solar system evolution, and the complex gravitational processes that continue to shape celestial architecture billions of years after the initial formation process concluded. The mystery that began with Percival Lowell's mathematical predictions over a century ago is finally approaching its resolution. The tools exist, the observations are being made, and the theoretical frameworks are in place to provide definitive answers about whether our solar system harbours a ninth planet. All that remains is for time, technology, and human persistence to reveal what secrets lie hidden in the frozen darkness beyond the orbit of Neptune. The technological arms race to find Planet 9 has transformed from a methodical survey project into something resembling a cosmic intelligence operation. Teams around the world are deploying increasingly sophisticated detection strategies, each designed to overcome specific challenges that have stymied previous searches. The hunt has evolved far beyond simply pointing telescopes at promising patches of sky and hoping for the best. Modern Planet 9 hunters employ what they call differential photometry techniques, comparing images taken months or years apart to identify objects that have shifted position against the stellar background. But this approach faces a fundamental challenge: distinguishing genuine planetary motion from the countless sources of false signals that plague deep sky observations. Consider the technical complexity involved in processing a single night's worth of data from a major survey telescope. Each image might contain millions of stellar sources, ranging from nearby stars in our own galaxy to distant quasars billions of light-years away. Cosmic rays striking the detector create bright spots that can mimic moving objects. Asteroids passing through the field of view generate tracks that must be carefully distinguished from the much slower motion expected from Planet 9. The data processing pipelines developed for these searches represent marvels of computational astronomy. Automated algorithms must identify genuine moving objects while filtering out instrumental artifacts, satellite trails, and the motions of known solar system bodies. Machine learning systems trained on millions of astronomical images can now recognize patterns that would take human analysts years to identify manually. Dr. Scott Shepard at the Carnegie Institution for Science has pioneered some of the most advanced techniques in this field. His team uses what they call the discovery machine approach, combining multiple detection algorithms to maximize their chances of identifying genuine trans-Neptunian objects while minimizing false positives. The system can process thousands of images automatically, flagging only the most promising candidates for human review. But even the most sophisticated algorithms struggle with the fundamental physics of Planet 9 detection. At the distances predicted by current models, the hypothetical world would appear to move so slowly across the sky that detecting its motion requires observations separated by years rather than months. This creates logistical nightmares for survey teams working with telescope schedules planned years in advance. The seasonal accessibility of different regions of sky adds another layer of complexity. Planet 9's predicted orbit would carry it through portions of the southern sky that are only observable during certain times of year from ground-based telescopes. Missing critical observing windows can delay confirmation of potential discoveries by entire years, creating agonizing periods of uncertainty for research teams. Some of the most promising search strategies focus on infrared wavelengths rather than visible light. If Planet 9 exists, it might emit detectable thermal radiation even if it reflects too little sunlight to be visible in optical surveys. The Spitzer Space Telescope conducted several searches for Planet 9's thermal signature before being decommissioned in 2020, setting important limits on how warm and large the hypothetical world could be. The upcoming James Webb Space Telescope represents an entirely new class of infrared capability that could revolutionize Planet 9 searches. Its unprecedented sensitivity to thermal emission could potentially detect a Neptune-sized world, even at the extreme distances predicted by some orbital models. The telescope's ability to observe continuously without the day-night cycles that limit ground-based surveys makes it particularly valuable for tracking slow-moving objects across long-time baselines. Ground-based infrared surveys face their own unique challenges. Earth's atmosphere glows brightly in infrared wavelengths, creating a background that can overwhelm the faint signals from distant solar system objects. Advanced adaptive optics systems and specialized filtering techniques help overcome these limitations, but they add complexity and cost to already challenging observational programs. The Atacama Large Millimeter Array in Chile has joined the Planet 9 search using radio wavelengths that could potentially detect thermal emission from a cold, distant world. ALMA's extraordinary sensitivity and angular resolution make it capable of detecting objects that would be invisible to other telescopes, but its limited field of view means that searches must be targeted toward specific predicted locations rather than conducting broad surveys. International collaboration has become essential for maximizing the efficiency of Planet 9 searches. Telescopes in different hemispheres can provide complementary coverage of the sky, allowing continuous monitoring of promising regions throughout the year. Data sharing agreements between major survey projects help ensure that potential discoveries aren't missed due to gaps in individual survey coverage. The Catalina Sky Survey, originally established to hunt for potentially hazardous asteroids, has become an unexpected contributor to Planet 9 research. While scanning for near-Earth objects, the survey regularly discovers trans-Neptunian objects that provide crucial data about the population and orbital distribution of the outer solar system. These serendipitous discoveries often prove more valuable than targeted Planet 9 searches. Similarly, the Linear program has contributed dozens of trans-Neptunian object discoveries while pursuing its primary mission of asteroid detection. The dual-use nature of these survey programs demonstrates how different areas of solar system research can support and reinforce each other in unexpected ways. The most ambitious Planet 9 search efforts are coordinating observations across multiple telescopes and wavelength ranges simultaneously. These campaigns can track potential candidates in real time, obtaining immediate follow-up observations that confirm or refute preliminary detections before the objects move too far to relocate. Dr. Chad Trujillo, who co-discovered several important trans-Neptunian objects, including Sedna, has developed search strategies specifically optimized for finding the most distant solar system inhabitants. His techniques focus on regions of sky where Planet 9's gravitational influence should be most pronounced, concentrating observational resources in areas most likely to yield definitive detections. The statistical challenges facing Planet 9 searches are as daunting as the observational ones. With hundreds of known trans-Neptunian objects now catalogued, researchers must develop increasingly sophisticated techniques for identifying genuine clustering patterns while accounting for selection effects and observational biases. Advanced Bayesian analysis methods allow astronomers to quantify their confidence in different orbital clustering scenarios while properly accounting for the uncertainties inherent in limited datasets. These techniques can distinguish between genuine astrophysical phenomena and statistical artifacts that might appear meaningful in small samples but disappear as more data becomes available. Monte Carlo simulations play a crucial role in testing whether observed orbital patterns could result from random chance. Researchers generate millions of artificial solar system configurations with randomly distributed objects, then determine how often these simulations produce clustering patterns as strong as those observed in the real data. The results of these statistical tests have evolved as the sample of known trans-Neptunian objects has grown. Early analyses based on small numbers of extreme objects showed strong evidence for non-random clustering. More recent studies incorporating larger samples have found weaker but still significant evidence for the patterns that inspired the Planet 9 hypothesis. Dr. Kevin Napier at the University of Michigan has conducted some of the most rigorous statistical analyses of trans-Neptunian object orbital distributions. His work suggests that while some clustering remains evident in current datasets, the statistical significance is lower than originally claimed and may not meet the threshold typically required for major astronomical discoveries. The ongoing statistical debate highlights fundamental questions about how much evidence should be required before accepting extraordinary claims in astronomy. The Planet 9 hypothesis represents exactly the kind of revolutionary idea that demands exceptional proof, but determining what constitutes sufficient evidence remains a matter of scientific judgment rather than mathematical certainty. Theoretical work has continued refining predictions about Planet 9's most likely properties and location. Computer simulations incorporating increasingly sophisticated models of solar system dynamics have narrowed the range of orbital parameters that could explain the observed trans-Neptunian object clustering while remaining consistent with other constraints. The latest theoretical models suggest that if Planet 9 exists, it most likely has a mass between 5 and 10 times that of Earth, and follows a highly elongated orbit with a semi-major axis between 400 and 800 astronomical units. These parameters place it at the very edge of detectability for current surveys, explaining why it has remained hidden for so long. Gravitational simulations spanning billions of years reveal how Planet 9's orbit might have evolved since the solar system's formation. These models suggest that the hypothetical world could have started in a much more circular orbit before being perturbed into its current elongated path by gravitational interactions with passing stars or other external influences. The simulations also predict specific signatures that Planet 9 should leave in the orbital distribution of smaller trans-Neptunian objects. These predictions provide testable hypotheses that can guide observational searches and help distinguish between genuine Planet 9 effects and alternative explanations for the observed clustering patterns. Advanced orbital integration techniques allow researchers to model the complex gravitational dance between Planet 9 and thousands of smaller objects over cosmic timescales. These calculations require massive computational resources and sophisticated algorithms capable of handling the chaotic dynamics that characterize the outer solar system. The theoretical work has revealed surprising connections between Planet 9 and other aspects of solar system architecture. If the hypothetical world exists, its gravitational influence might explain not just the clustering of extreme trans-Neptunian objects, but also the unusual orbital inclinations observed in some Kuiper belt populations and the apparent deficit of objects in certain orbital resonances with Neptune. Some models suggest that Planet 9 could be responsible for the surprising number of highly inclined trans-Neptunian objects, worlds whose orbits are tilted at steep angles relative to the plane of the solar system. The gravitational perturbations from a distant massive planet could gradually pump up orbital inclinations over millions of years, creating the observed population of tilted objects. Even more intriguingly, Planet 9 might explain the existence of retrograde trans-Neptunian objects that orbit the Sun in the opposite direction from the planets. These backward-orbiting worlds represent some of the most extreme dynamical environments in the solar system, requiring exceptional circumstances to achieve their unusual orbital configurations. The theoretical framework developed for Planet 9 research has applications that extend far beyond our own solar system. The same gravitational mechanisms that could shepherd trans-Neptunian objects into clustered orbits might operate in exoplanetary systems, creating detectable patterns in the distribution of debris disks around other stars. Astronomers studying debris disks around nearby stars have begun looking for the kinds of asymmetries and gaps that might indicate the presence of unseen planets. The techniques developed for analyzing Kuiper belt structure are being adapted to search for similar patterns in these distant planetary systems. The Planet 9 hypothesis has also influenced theoretical work on planetary formation and migration processes. If our solar system once contained additional giant planets that were ejected into interstellar space, similar events might be common during the formation of other planetary systems. Computer simulations of planetary system formation now routinely include the possibility of planetary ejection and capture events. These models suggest that many stars might acquire or lose planets through gravitational interactions, creating a galactic ecology where worlds can migrate between different stellar environments. The implications for astrobiology are particularly fascinating. If planets can be exchanged between star systems, they might carry organic compounds or even living organisms across interstellar distances. A captured Planet 9 could potentially harbour biosignatures from its original stellar system, providing a unique window into the chemistry of alien worlds. Recent advances in computational power have enabled increasingly sophisticated simulations of these planetary migration processes. Modern supercomputers can model the gravitational interactions between hundreds of planets and planetesimals over billions of years, revealing the complex pathways through which planetary systems can evolve and reorganize. The results suggest that our solar system's current architecture might be highly unusual, with most planetary systems experiencing more dramatic episodes of migration and ejection than we have traditionally assumed. If correct, this would make Planet 9 not an anomaly, but a typical example of the violent processes that shape planetary system evolution. These theoretical insights are being tested against observations of exoplanetary systems discovered by the Kepler Space Telescope and other survey missions. Many of these systems display orbital architectures that would have seemed impossible just a few decades ago, with giant planets orbiting extremely close to their stars and multiple planet systems locked in complex chains of orbital resonances. The diversity of exoplanetary system architectures provides crucial context for understanding whether Planet 9 represents a plausible outcome of solar system formation processes. The discovery of free-floating planets drifting through interstellar space demonstrates that planetary ejection events are not merely theoretical possibilities, but observable phenomena occurring throughout the galaxy. As the search for Planet 9 continues with ever more sophisticated techniques and instruments, the broader implications of the investigation continue to expand. Whether the hypothetical world exists or not, the search has already revolutionized our understanding of the outer solar system and the complex gravitational processes that continue to shape planetary orbits billions of years after formation. The techniques being developed for Planet 9 detection are finding applications in searches for other elusive objects, from potentially hazardous asteroids to the hypothetical Oort cloud comets that might threaten Earth. The statistical methods pioneered for analyzing orbital clustering are being adapted to study everything from galaxy formation to dark matter distribution. Most importantly, the Planet 9 saga exemplifies the best aspects of modern astronomy: the combination of theoretical prediction and observational verification, the international collaboration required for major discoveries, and the willingness to pursue extraordinary possibilities based on subtle patterns in complex data. The resolution of this mystery, whatever form it ultimately takes, will mark a defining moment in our understanding of the solar system we call home. Every observation brings us closer to answers that will either reveal a hidden world reshaping our cosmic neighborhood or teach us important lessons about the limitations and possibilities of astronomical inference. The universe maintains its silence about Planet 9's existence, but human ingenuity and persistence continue their patient assault on this cosmic mystery. Advanced instruments scan the sky with unprecedented precision. Computer algorithms process vast datasets with superhuman efficiency, and theoretical models explore every possible explanation for the patterns that have captivated astronomers for nearly a decade. Somewhere in the data already collected or in observations yet to be made lies the answer to one of astronomy's most compelling questions. Whether that answer reveals a massive world lurking in the outer darkness, or demonstrates the subtle ways that incomplete information can lead us astray, the truth will fundamentally advance our knowledge of the cosmic environment we inhabit. The hunt continues, driven by the tantalizing possibility that the next clear night might bring the observation that changes everything we thought we knew about our solar system's architecture. In observatories around the world, dedicated researchers maintain their vigil, knowing they're participating in one of the most significant investigations in the history of planetary science. The clock ticks toward resolution, measured in gigabytes of data and algorithmic refinements rather than calendar pages. Every photon captured by sensitive detectors, every orbital calculation performed by powerful computers, every statistical analysis applied to growing datasets brings us incrementally closer to understanding whether our solar system contains a ninth world worthy of the name. When that understanding finally emerges, it will represent more than just the discovery or non-discovery of another planet. It will demonstrate once again that the universe is stranger, more complex, and more surprising than we ever dared imagine. The search for Planet 9 embodies humanity's endless quest to understand our place in the cosmos, one observation at a time, one theory at a time, one mystery at a time. The darkness beyond Neptune may yet yield its secrets to human curiosity and technological prowess. Whether those secrets include a hidden world or reveal more subtle truths about the nature of our cosmic neighborhood, the answer will mark another milestone in our species' long journey toward understanding the universe that gave us birth and continues to challenge our most fundamental assumptions about reality itself. The final act of our cosmic detective story unfolds not in dusty archives or theoretical papers, but in the most advanced observatories humanity has ever constructed. Right now, as you process these words, the Vera Rubin Observatory in Chile stands as a technological cathedral dedicated to a single purpose: mapping the southern sky with unprecedented precision and revealing whatever secrets hide in the darkness beyond Neptune. This isn't just another telescope, it's a game-changer designed specifically for the kind of systematic, repeated observations that Planet 9 detection demands. The facility houses the largest digital camera ever built, a 3.2 gigapixel marvel containing 189 individual sensors that can capture images covering an area of sky 40 times larger than the full moon in a single exposure. When Rubin begins full operations, it will revolutionize our approach to finding moving objects in the outer solar system. Every few nights, it will photograph the entire visible southern sky, building up a database of stellar positions and motions that will dwarf every previous astronomical survey combined. If Planet 9 exists anywhere within the survey area, this systematic approach should reveal its presence within the first few years of operation. Dr. Jeliko Ivazic, the director of Rubin Observatory, describes the facility's impact in terms that border on the revolutionary. The telescope will generate approximately 20 terabytes of data every single night, creating what he calls a movie of the universe that captures how celestial objects move and change over time. For Planet 9 hunters, this represents the difference between searching for a needle in a haystack and having a machine that can systematically examine every piece of straw. The observatory's automated detection systems will identify millions of moving objects, from nearby asteroids to the most distant inhabitants of the trans-Neptunian region. Machine learning algorithms specifically trained for this task will filter through the data streams, flagging objects that display the slow, steady motion characteristic of distant planets, while eliminating false signals from cosmic rays, satellite trails, and instrumental artifacts. But Rubin Observatory represents just one element of a coordinated global effort that's transforming Planet 9 research from educated guesswork into precision science. The James Webb Space Telescope has joined the hunt, using its unprecedented infrared sensitivity to search for the thermal glow that even a cold, distant world might emit. Unlike previous space telescopes that operated in visible light, Webb can detect heat signatures that would be completely invisible to ground-based surveys. The strategy behind these infrared searches reflects sophisticated understanding of how Planet 9 might appear to our instruments. Even at temperatures approaching absolute zero, a massive world would retain enough internal heat from its formation to emit detectable radiation at specific wavelengths. Webb's extraordinary sensitivity could potentially spot this thermal signature, even if Planet 9 reflects too little sunlight to be visible in optical surveys. Ground-based facilities have developed their own innovative approaches to the detection challenge. The Subaru telescope in Hawaii uses advanced adaptive optics systems that can compensate for atmospheric turbulence with incredible precision, essentially creating space telescope quality images from the ground. This capability allows astronomers to detect fainter objects and track smaller movements than would be possible with conventional ground-based observations. The systematic nature of these modern searches represents a fundamental shift from the somewhat haphazard approach that characterized earlier Planet 9 efforts. Instead of pointing telescopes at promising regions and hoping for lucky discoveries, contemporary surveys follow carefully planned strategies that maximize coverage while minimizing the chances of missing potential detections. Dr. Mike Brown, one of Planet 9's most dedicated advocates, estimates that these combined efforts have already ruled out roughly 78% of the regions where the hypothetical world might be hiding. Each negative result constrains the remaining possibilities, gradually cornering Planet 9 into an ever-shrinking region of parameter space where it could potentially exist. The process resembles a cosmic game of elimination, where every failed detection provides valuable information about where Planet 9 isn't, even if it doesn't reveal where it might be. This systematic approach ensures that when definitive results finally emerge, they'll be based on comprehensive rather than selective evidence. Advanced computer simulations play an increasingly crucial role in guiding these observational efforts. Researchers can now model the gravitational evolution of the outer solar system with extraordinary detail, predicting exactly how Planet 9's presence would affect the orbits of thousands of smaller objects over billions of years of cosmic time. These simulations reveal the subtle fingerprints that a massive distant planet would leave throughout the trans-Neptunian region. They predict not just where extreme objects should cluster, but also where gaps should appear in orbital distributions, how inclinations should be modified, and what kinds of resonant relationships should emerge between Planet 9 and the smaller bodies under its gravitational influence. The theoretical framework has become sophisticated enough to make specific, testable predictions about phenomena beyond simple orbital clustering. If Planet 9 exists, it should create detectable asymmetries in the distribution of Kuiper belt objects, influence the orbital evolution of certain comet families, and possibly explain the unusual abundance of highly tilted trans-Neptunian objects that have puzzled astronomers for years. Each of these predicted effects provides an independent test of the Planet 9 hypothesis, creating multiple lines of evidence that must all point in the same direction if the theory is correct. This multifaceted approach helps distinguish between genuine gravitational influences and statistical artifacts that might appear significant in individual datasets but fail to show up consistently across different types of analysis. The international scope of current Planet 9 research reflects the global nature of modern astronomy and the recognition that resolving this mystery requires resources and expertise from institutions worldwide. Survey teams from the United States, Chile, Australia, Japan, and Europe are sharing data and coordinating observations to ensure comprehensive coverage of the sky regions most likely to harbour the elusive world. This collaborative approach has already paid dividends in the form of new trans-Neptunian object discoveries that provide crucial test cases for Planet 9 theories. Each newly discovered extreme object adds another data point to the statistical analyses that either support or challenge the orbital clustering evidence. The growing database allows researchers to test their hypotheses against increasingly robust datasets that minimize the selection effects and observational biases that plagued earlier studies. Perhaps most remarkably, some research teams are developing search strategies specifically designed to find Planet 9 regardless of which formation scenario proves correct. These approaches focus on detecting the gravitational signature of a massive distant object rather than looking for specific types of clustering or orbital modification that might result from particular theoretical models. The gravitational lensing technique represents one such model-independent approach. If Planet 9 passes in front of distant stars as viewed from Earth, its gravity could bend the starlight in ways that create detectable, brightening events. While such alignments would be extraordinarily rare, systematic monitoring of millions of background stars might eventually reveal the characteristic signature of a massive object moving through the outer solar system. Other teams are exploring the possibility that Planet 9 might have captured its own system of moons during its hypothetical ejection from the inner solar system. These satellites, if they exist, might be more easily detectable than Planet 9 itself, providing an indirect way to locate the primary world by finding its gravitational companions. The moon hunting approach gains credibility from observations of other trans-Neptunian objects that possess substantial satellite systems. Pluto's family of moons demonstrates that complex gravitational architectures can survive the violent processes that shape the outer solar system. A much more massive Planet 9 might have retained or captured an even more extensive system of companions. Cutting-edge statistical techniques are being developed specifically to handle the complex datasets generated by modern Planet 9 searches. Traditional astronomical analysis methods were designed for studying individual objects or small samples, but contemporary surveys discover hundreds of trans-Neptunian objects annually, creating datasets that require entirely new approaches to extract meaningful patterns. Machine learning algorithms trained on millions of simulated orbital configurations can now identify subtle clustering patterns that would be invisible to conventional statistical tests. These systems can process vast amounts of orbital data while properly accounting for the selection effects and observational biases that complicate traditional analyses. Bayesian inference methods allow researchers to quantify their confidence in different Planet 9 scenarios while incorporating uncertainties from multiple sources. These techniques can distinguish between evidence that genuinely supports the Planet 9 hypothesis and patterns that might appear significant but could easily result from random chance or systematic errors. The statistical sophistication of contemporary Planet 9 research reflects broader trends in astronomy toward big data approaches that can handle the information deluge created by modern survey instruments. The same techniques being developed for Planet 9 analysis find applications in studies of galaxy formation, dark matter distribution, and exoplanet detection. As these various search strategies converge on the same regions of sky and parameter space, the Planet 9 mystery appears to be approaching its resolution. The combination of systematic surveys, advanced instruments, and sophisticated analysis techniques has created an unprecedented capability for detecting distant solar system objects that would have been completely invisible to previous generations of astronomers. Dr. David Jewett, one of the discoverers of the Kuiper Belt, describes the current moment as potentially decisive for Planet 9 research. The observational and theoretical tools have finally reached the level of sophistication needed to provide definitive answers about whether a massive ninth planet lurks in the outer darkness of our solar system. The implications of resolving this mystery extend far beyond satisfying scientific curiosity. If Planet 9 exists, its discovery would fundamentally transform our understanding of how planetary systems form and evolve. It would provide direct evidence that our solar system experienced violent episodes of planetary migration and ejection during its early history, validating theoretical models that have been developed to explain the bizarre architectures observed in many exoplanetary systems. The existence of Planet 9 would also raise profound questions about its origin and composition. A super-Earth in the outer solar system would represent a missing link in planetary formation theory, demonstrating that our cosmic neighborhood once contained examples of the most common type of planet found around other stars. Understanding how such a world came to exist in its current location would provide crucial insights into the chaotic processes that shape the solar system's architecture. Alternatively, if Planet 9 proves to be a captured rogue planet, its discovery would demonstrate that planetary systems can exchange members across interstellar distances. This possibility has fascinating implications for astrobiology, suggesting that organic compounds or even living organisms might occasionally travel between star systems aboard wandering worlds. The chemical and isotopic composition of a captured Planet 9 would preserve a record of the stellar environment where it formed, providing a unique opportunity to study the chemistry of an alien solar system without leaving our own cosmic neighborhood. Such a world might harbor subsurface oceans heated by tidal forces or radioactive decay, creating potential habitats for exotic forms of life adapted to extreme conditions. Even the failure to find Planet 9 would represent a significant scientific advance, demonstrating that the orbital clustering of extreme trans-Neptunian objects results from more subtle processes than initially suspected. This outcome would highlight the importance of observational biases and selection effects in astronomical research, while opening new avenues for understanding the complex gravitational dynamics that operate in the outer solar system. The resolution of the Planet 9 mystery will also provide crucial validation or refutation of the statistical techniques and theoretical frameworks that have been developed specifically for this investigation. These methods are already being applied to other areas of astronomy, where subtle patterns in large datasets might reveal hidden phenomena. As we stand on the threshold of potentially revolutionary discoveries, the Planet 9 search exemplifies everything that makes modern astronomy compelling. It combines the romance of exploring our own cosmic neighborhood with the technical sophistication of 21st century science. It demonstrates how theoretical predictions and observational verification work together to advance human knowledge of the universe. The mystery that began with Percival Lowell's mathematical obsessions over a century ago has evolved into one of the most systematic and comprehensive investigations in the history of planetary science. Whether it culminates in the discovery of a new world or teaches us important lessons about the limitations of astronomical inference, the outcome will mark a watershed moment in our understanding of the solar system we inhabit. Every clear night brings new data that inches us closer to resolution. Advanced algorithms process the information streams from multiple telescopes, searching for the subtle patterns that might betray Planet 9's presence. Theoretical models continue to refine their predictions about where the hypothetical world might be found and what its discovery would mean for solar system science. The universe maintains its enigmatic silence about Planet 9's existence, but human ingenuity and technological capability continue their patient assault on this cosmic mystery. We've developed the tools to find virtually any massive object that might be hiding in the outer solar system. The question is no longer whether we can detect Planet 9 if it exists, but whether it exists to be detected. Somewhere in the vast darkness beyond Neptune, the truth waits to be discovered. Whether that truth involves a hidden world that will rewrite textbooks and transform our understanding of planetary formation, or a more nuanced explanation for the patterns that have captivated astronomers worldwide, the answer will emerge from the marriage of human curiosity and technological prowess that defines modern science at its best. As we reach the end of our journey to the edge of everything we know, the mystery of Planet 9 remains tantalizingly unresolved. But perhaps that's exactly as it should be. Science thrives on questions that push us to the very limits of our technological capabilities and theoretical understanding, and Planet 9 represents both in their purest form. Whether the darkness beyond Neptune conceals a massive world reshaping our solar system's architecture, or holds more subtle truths about the gravitational processes that continue sculpting planetary orbits billions of years after formation, we stand on the threshold of answers that will fundamentally change how we understand our cosmic home. The hunt continues with unprecedented precision and sophistication, driven by humanity's endless curiosity about the universe that gave us birth.